Precalculus statistics overview of lesson 4. This is called the normal distribution. So 14.4. We say that data is normally distributed if it approximately follows this kind of a shape. I got a little bit off there, but approximately follows that kind of a shape where this right here in the middle is our average. I guess if I'm saying we're dealing with all of the data, I'll go ahead and use mu. So it's the mean, the average of all of the data points that are available. And you have a relatively high percentage of the data that is close to the average. And the farther away from average you get, the fewer data points there are. And a lot of stuff follows the normal distribution. The normal distribution. Sometimes also called a bell curve. For example, if you took like what the average height of a person in the world is, and then you collected all of the heights of people, the majority of people are relatively close to the average, and then the taller and taller and taller and taller you get fewer and fewer and fewer people. And the shorter and shorter and shorter and shorter you also get fewer and fewer and fewer people. And the way that this normal distribution works is we can, well, let me put maybe like a data point about like this, that this would be mu plus 1 sigma. And then like out here would be mu plus 2 sigma. And then down here would be mu minus 1 sigma, mu minus 2 sigma. So what's going on with this? Sigma, again, is the standard deviation. It's how far from the average the data points typically lie. And there are certain percentages of the data that fall within a certain range of how far above or below the average you are. So for example, if you're going plus or minus 1 sigma, then you get 68.3% approximately of the data falls in this range, from the average below and the average above by 1 standard deviation. Then if you're going 2 standard deviations above and below, you get about 99.5%. About 99.5% of the data lies in that range. If you go all the way out to 3 standard deviations above and below, so mu plus 3 sigma, and then down here we have mu minus 3 sigma, then here we get a good 99.7% of the data. And because so many different things are normally distributed, and when you get into statistics kind of stuff, I don't know if you would get into like a kind of a typical elementary statistics undergrad course, but when you get into a little bit more of the analyzing stuff, there's some tools that you can use to evaluate how well or how close is my data to following a normal distribution? So how much can I trust these kinds of percentages? But what we have is a tool for analyzing like how many data points fall under certain ranges. And let me switch over to these tables here. Well, let me start with this one. So this would be a Z table that gives us what percentage of the data is in the shaded area, where the middle is our mu. In this case, it's dealing with the mu of 0, but the percentages work if we have a different value. And then this would be plus 1 sigma. This would be plus 2 sigmas. This would be minus 1 sigma. So this gives us the values of what percentage. So the values inside the table are percentages represented as a decimal. And then what percentage of the data is in the shaded area. So this is a cumulative distribution where notice what I was showing you earlier was how far above and below the middle. This is just how far below the value you are, where we're only adding fractions of sigma. So for example, if you are like the shaded part that is currently showing is showing adding 1 sigma. So if we go, the way this is read is this is 1 point, and the first column is 1.0. Then the second column is 1.1, and third column is 1.2, and then 1.3, 1.4, 1.5. That's what the different columns are for. So if we're looking at exactly 1.0, then what we can say is, if I do red here, 84.13% of the data is below one is at or below 1 standard deviation above the average, is how to read that. So here we are doing the adding, we're going above the average, and then this table here, we are subtracting, that's what the negatives are for, we're going below the average. And so kind of a formula that ends up getting used a lot in this kind of a context is x bar plus or minus T sigma. Or kind of how we're dealing with it here, it's mu plus or minus Z sigma. Your textbook uses this x bar plus or minus T sigma. Here we're using mu plus or minus Z sigma. So the way this works, I'm going to jump into a homework problem, and you can kind of see how this works. I'm using tables that are slightly different from what the textbook gives you, and I'll give you tables like this for a problem. So I'm going to do number 13 here. So here's what we have. We have a set of data. It's normally distributed, okay? These formulas and these tables only work if the data is normally distributed, if it follows this kind of a pattern, all right? And it's normally distributed with a mean of 140. So we're going to say we know that mu is 140. We don't know if this is a population average or a sample average. I'm going to assume it's a population average. And a standard deviation of 20. And we want to find first, what percent of the data is between, what percent of the data is between, is between 100 and 150. Okay, so here's where it takes just a little bit of analyzing to see what's going on. So I think it could be very helpful to sketch a little thing. The more wide it is, it would be a larger standard deviation, and then a very small standard deviation would be more like that. I'm not really trying to represent that. That's just an actual tidbit. So here's what we know. Our average is 140. Okay, so I want to find what percentage of the data is between 100 and 150. So I'm looking for what percentage of the data is between those values. Well, let's look at how many sigmas, how many standard deviations I'm going down, and how many standard deviations I'm going up. So if I'm starting at 140, that's my middle, then I'm going down to 100. How many standard deviations? Well, I can say, well, you can set up as a formula and solve. We can say 140 minus Z times the standard deviation of 20 equals 100. We want to see from our average, from mu, how many standard deviations do I have to subtract? So standard deviation is 20 to get down to 100. So when you solve, you would get negative Z times 20 equals negative 40. So then you get that Z is 2.0. Then we can look at how many standard deviations up are you going, and we could set up the same thing up, but we're going to do a plus. So 140 plus Z sigma equals 150, and when you solve, we are adding 0.5. So what we can do is we can go to our distribution tables, and here's what we can see. If we are subtracting 2, we get this value right here, 0.0228. 0.0228. Now, this is a cumulative distribution table. It's not going out from the middle. So what that means is this right here is 0.0228. So if you go down 2 sigmas, the amount of data below that is 0.0228. And then if we go look at what's happening if you go up 0.5 for z, if we go up 0.5 for z, that is going to be up going 0.5, that is going to be 0.6915, 0.6915. I don't know if you can see those numbers. I don't know if this, hopefully it's not too small. 0.6915. So what that is, if I kind of sketch a little mini version of what we have, of here's 150, and 0.6915 is everything below that. 0.6915. So I want everything below 150, but only down to 100. So I need to subtract out that 0.0228. So minus 0.0228. And when you do that, you do so we're doing 0.6915 minus 0.0228. And we do that 0.6915 minus 0.0228, and we get 0.6687, which as a percentage would be 66.87%. So we can say that 66.87% of the data is between 100 and 150 if this is normally distributed. Okay? And there are other things. I'll mention also percentile. Percentile. These are percentiles that these tables have. A percentile is you're saying X percent of the data is below this. So like when you take the SAT, if you score in the 92nd percentile, that means you scored better than 92% of the students. So that is this kind of a distribution here. That's this kind of a distribution. So 92nd percentile would be like wherever you are here, such that 92% of the data is of the test takers scored below you. Oops, erased more than I wanted to there. I guess this is the problem with writing on top of a picture. I don't know if I can erase the writing without erasing the picture. Anyway, so like for this problem, we have the question, find the limit above which 90% of the data lies. So I got to add one more page here. Hold on a second. Sorry. I thought that 5 would be enough for all of what I'm doing, but it's because I added a couple more things. Okay, that'll work. So this is still number 13. This is number 14, part C. I want to do that. Number 13, part C, is find the value that defines the 75th percentile. So we want to go to our cumulative distribution table and look at where do we have a p-value of 75%. 0.75, 0.758, 0.75. The thing that is closest to 0.75 would be this one. Although, depending on the context, you might be like, well, I want the value that is higher than 75% rather than lower than 75%. Because, like, I really want to, I would actually go more that direction to say, I want to make sure that I am not undershooting things, I'd rather overshoot things. So we need to add what? We need to add 0.68. We need to add 0.68 sigmas. So I'll go back over here and I'll say, so what we have is we need mu plus 0.68 sigma. So my average was 140, and I need to add plus 0.68. Sigma was 20. And when you do that math, we do 140 plus 0.68 times 20, and we get 153.6. So whatever this data is representing, if you are at 153.6, you are in the 75th percentile, meaning you are better or you have a value that is bigger than 75% of the other data points. Okay? So that's the kind of stuff that goes on there.